This is scenario number 2. In this scenario, we're going to neutralize our weak acid with 17.5 milliliters of sodium hydroxide, and the concentration of that sodium hydroxide solution is 0.150 molar. To solve this problem, you write down the reaction between acetic acid, HC2H3O2, and sodium hydroxide. I just write down the hydroxide portion of the sodium hydroxide and show what they produce. That's an acid-base reaction, so the acid will donate its proton to the hydroxide, and you'll be left with a conjugate base, C2H3O2-, and a water molecule. You should work in moles in this problem. So I'm going to write down the moles of acetic acid that I have. I'm going to write down how I'm going to get these moles, but then I'm going to be erasing how I determined that. So the way that I determine the moles of acid is I write down the molarity of the acid, 0.150 moles per liter, and I'm just going to multiply that by the volume of the sample in liters. It's a 35 milliliter sample, so I'll multiply it by 0.035 liters. That gives me 0.00525 moles of the acid. I will write down that number underneath the moles of acid, or underneath the formula for the acid. 0.00525 moles. I'll do the same thing for the base, but I'll just talk you through this one. The molarity of the base is 0.150 molar. I'm going to multiply that by this 17.5 milliliters, but written in liters, and that gives me the moles of hydroxide. That number is 0.002625 moles. Let me just erase this portion down here. At this point in time, nothing has happened, so I don't have any products yet. But when they react, I'm going to lose, the acid and the base will react until one of them disappears. And I have less hydroxide. So I'm going to subtract each one of these mole values by the number of moles of hydroxide I have. So I'm going to subtract 0.002625 from both of these, 0.02625. And I'm going to add that to my product side, 0.002625. I don't have to worry about the water because it's not contributing to the pH at all. So when all is said and done, I will have, when I subtract these front two, I have 0.002625 moles of acetic acid left. I have no hydroxide left because it completely reacts. And I gain 0.002625 moles of my conjugate base. I now have a buffer because I have a weak acid and its conjugate base in the container at the same time, and I've gotten rid of my hydroxide. You can put these mole values that are written here directly into Henderson-Hasselbalch to solve for the pH of the buffer. Alternatively, you can divide these both by the total volume in our container, which is now going to be 35 milliliters plus the 17.5 milliliters of hydroxide that we've added. So that gives you a total of 52.5 milliliters, or 0.0525 liters. I'll divide each of these mole values by that volume, 0.0525 liters, 0.0525 liters, and that gives me a molarity of my acid and a molarity of my base. Both of them are going to have the same value, 0.0500 molarity and 0.0500 molarity. Let me just get rid of this down here. One thing I like to do at this point is just remind myself which is the acid and which is the base. This molarity on the left-hand side is the acid, the one on the right-hand side is the conjugate base. I will put those into Henderson-Hasselbalch, and pH equals negative the log of the Ka of the acid, 1.8 times 10 to the negative fifth, molar plus the log of the concentration of the conjugate base over the concentration of the acid. So this ends up equaling negative the log of 1.8 times 10 to the negative fifth. The pH is now 4.74. Compared to scenario number 1, we're now a little bit more basic. The gist of this problem is to just think about particles. So think about how many particles of acid you had originally, how many particles of base you added, react them together and figure out what you have left. And if you have the weak acid left and you have some conjugate base produced, you have a buffer, use Henderson-Hasselbalch. That's the gist of scenario number 2. See the next video for scenario number 3.